So the last of our different trig relationships, the products to sums. So it's useful when we want to turn the product of two trig functions, and we're mainly talking about sine and cos here, and turn it into the sum of two trig functions. So the first one's this: 2 cos cos ends up being cos A minus B plus cos A plus B. It basically comes from our cos alpha plus beta formula, if you like. And that's how we know it must be a cos plus a cos here, because cos cos was in the cos expansion. I would always start with A minus B. I mean, it doesn't matter, because of course it's plus, it could go in any order. But there is a reason why, and we'll see that in a sec. If I have sine cos, well that must have come from the sine alpha plus beta formula. And so, again, I would put the difference first, but again, it doesn't matter. But when we come to the third one, when it's sine sine. Now sine sine also comes from the cos one, but you'll notice it's minus. And that's why I always like putting the difference first, because then I just remember, I'm always going to start with the difference. And then with the sine sine, okay, I know it comes from cos, but it's different. And so that's how I know, oh, it's the difference. That one's minus. That's how I think about it when I'm trying to remember which of these formulas are. Now, having said that, remember, these formulas are on the reference sheet. So if you ever get, oh, hang on, which one was which, you can always look it up and go, okay, I'll make sure I've got the right one. Now, if I've got something like this, and I want to express this product as the sum or the difference of two trig functions. Now, I've deliberately written it as cos sine rather than sine cos, just to point something out. If I see it as cos sine, I want to rewrite it, because remember, it's A minus B, so the order actually is important. The sine has to go before the cos. So when I write it that way, I can go, okay, it's the sine of the difference, x minus 5x, and then the sine of the sum, x plus 5x. Now, why is that important? Because I end up with sine minus 4x, but of course sine is an odd function, so that would be the same as minus sine 4x. Cos cos, well, that one comes from the cos function, but actually our formula is 2 cos cos, not cos cos. So I've got a half of our formula. So a half of 2 cos cos, and then we get the cos of the, wow. Notice I said start with the difference, but this one's highlighting, well, it doesn't actually matter because it is a sum. So I could have done the sum first and then the difference second. I'm still going to get the same answer for this one. Cos of minus 2 theta, well, cos is an even function, so that would be the same as cos 2 theta. If I wanted to work out 2 sine 45 cos 15 without using my calculator, then I go, okay, well, that's sine cos. It's going to be sine 45 minus 15, sine 45 plus 15, sine 30, sine 60. We've got exact ratios for those, and there's my answer. 1 plus root 3 on 2. I want to prove this identity here. Sine squared 5 theta minus sine squared 3 theta is sine 8 theta sine 2 theta. And I think this is one where I'm going to start with the right hand side rather than the left hand side, because I've got the product here. I want to turn it into, well, the difference of two things. So I want to change that product to a difference. So it's going to be a half of that formula, because remember our formula is 2 sine sine. So I get a half of cos of the difference minus, because it's difference, cos 8 plus 2 theta. Still not quite there. How am I going to get these? Well, now I'm going to make use of double angle formulas to get the squared in there. So cos 2 theta, 1 minus 2 sine squared theta. So in this case, cos of 6 theta will be 1 minus 2 sine squared 3 theta minus 1 plus 2 sine squared 5 theta, and eventually we get our final answer there. Going back the other way then, how do I go from sums to products? Sine plus sine, I want to add those together. This is what we end up with. 2 sine half sum cos half diff. These ones are easier to remember. So 2 sine half sum cos half diff. We're going the other way this time. So this time, instead of starting with the difference, I finished with the difference, so we're going back the other way. 2 sine half sum cos half diff. Cos plus cos, 2 cos half sum, cos half diff. Notice they both finish with the cos half diff. They start with the same ratio that I'm talking about. So sine started with the sine, cos started with the cos. But then we get cos minus cos, and this one becomes minus 2 sine half sum, sine half diff. Well, it's the difference. So this one's difference. Everything's different. Instead of 2, it's minus 2. Instead of being the same ratio to start with, I go to the other ratio. So it's sine. And instead of finishing with cos, I finish with sine. Everything's different. It's different. Now the thing about these ones, these are not on the reference sheet. They are if you read the other ones backwards, I suppose. So they don't specifically have these ones. So if I now want to prove this one, cos 75 plus cos 15 over sine 75 minus sine 15 equals root 3. And because I've been asked to prove it, I can't just simply go to my calculator and go, oh look, it's the square root of 3. I want to prove this. Well, the first thing I'm going to do is change the denominator to be plus sine of negative 15. Because you'll notice I don't have a formula there for sine minus sine. So I make it sine plus sine by making the use of it being an odd function. But now on the top, cos plus cos, 2 cos half sum, cos half diff. And then on the bottom, 2 sine half sum, cos half diff. Well, there's a bit of cancelling that's going to happen there. The 2's will obviously cancel, but so will these cos half of 90, they're going to cancel, and I'm left with cos of 30 over the sine of 30, which is the same as the cot of 30, and that's the square root of 3. So we get our answer. I want to solve this equation. Sine x plus sine 3x is equal to 0. So when it's equal to 0, the really nice thing is, if I can write things as a product, like quadratic equations, how do we solve those? Well, if a times b equals 0, I know either a is 0 or b is 0. So if I can write this sum as a product, that's going to make my life a lot easier, because I know one of those products must equal 0. So sine plus sine, 2 sine half sum, cos half diff, that's going to equal 0. Cos is an even function, so I can make that cos x. And I end up with 2 very simple equations. Because when we're talking about sine or cos equaling 0, we know they're the boundary values. So sine 2x equals 0, I'll get 0, 180, 360, but it's 2x, so I'm going around twice. I'll also have 540 and 720. Divide all those by 2. Now let's see if cos x equals 0 creates some more possibilities. There's only 2 of those, 90 and 270. Oh, well, we already had those, so it didn't create any new solutions, but it's still important that we check it, because you never know, it might. There's our list of solutions to this equation. Sums to products, products to sums.